Okay, so I'm going to go through an example program from the book, which has to do with computing the so-called Chebyshev bias. So the idea brought forth by Chebyshev is that if you look at the primes, then there is a tendency that they have remainder 3 mod 4 more often than 1 mod 4. So of course, if you have a prime, then usually it's it's an odd number. The only uh, uh, exception is 2. So the whole idea is that you sort of take the primes and you put them into piles, and then you sort of see which pile is bigger. So in order to say something about this, we show a simple-minded experiment. And I'm showing you this as an example of some of the control structures, but also actually as an example of the efficiency later principle that I tried to sell in the last little movie. And this is a good example of a highly inefficient program that nevertheless is fairly easy to write. Okay, so the first part of the program is called remainder list, and it's defined like this. This is an example of a procedure which is straightforward in input and output. It has only local variables, so they're defined over here, n and cn, and it's something that takes a number as an input and makes a list, and then takes this list and returns that as the output. So before I explain how it works, let me show you, just move this up from here. Let me show you how an example would look like. So what I've done is that I've asked Maple to look at the first 100 primes and then compute the remainder mod 4 of those. So you see in the very beginning you have 2, because that's 2 mod 4. And then next time I have 3 mod 4, giving 3. The next prime is 5, gives me 5. 1 mod 4, next prime is 7, that's 3 mod 4, and so on. And the idea that Chebyshev is suggesting is that there are more 3s than there are 1s as the number of primes go to infinity. So how does this work? Well, there's a construct that we're going to use many times in the course, which is sort of an efficient way of collecting information in a list. And the syntax for this, we're coming back to it next week, but the syntax for this is a little bit odd, so let me explain it carefully. So I start by defining a list to be empty. So that's what we have here. Cn is the empty list, so it just means that we have a list with no elements in it. And then there's a for loop, so the for loop repeats something a given number of times, right? So when I ran the program just before, the number was 100, and then using a built-in construction in Maple called ith prime, I can run through the first 100 primes. So the ith prime just means that if I run ith prime with n, I get prime number n starting from number 2 starting from the prime 2 as number 1. But the construction, so what you see here is the computation of the remainder mod 4 of the ith prime. But the construction here is what I really want you to notice, because it's an efficient way of collecting data that we will use many times, and it's perhaps not super obvious what it's supposed to mean. So the way it works is that it takes the newly computed remainder, so a number 1, 2, or 3, and puts it at the end of the list, right? So in the beginning of the program, I had an empty list. The first time I run this, I will put 2 into the list. The next time I run it, I will put 3 at the end of the list. Then I have 1 at the end of the list, and so on. So the list will keep growing until you have this complete list that I saw here if you run it with 100. And the way it works, let me show you what op does. So I will run like this. So op is an operation in Maple that, among other things, takes a list and pulls out the content of the list. Right? So up of a list is the sequence of numbers in that list. So when I apply up to the list that I just computed, essentially what happens is that the brackets will disappear. So that's what I'm doing up here, right? So essentially what this means is that I have my list, I forget that it's a list, and then I put it back into a new list, right? So this is what's happening here. So the net effect of this of these commands is that I will append the newest computation at the end of my list, right? So I will take my list, I pull it out of the list as a sequence, and I put it back as a list, but then I put in another term at the very end. That's how this works. And this is a popular way of doing computations in Maple, in particular because it's fairly fast. So I mean, this is something that could be very slow in other programming languages actually, but in Maple it works well. Okay, so that's how this works, right? So you can see essentially it just runs through the 100 iterations and collects all the data in this list. Okay, so this is one part of the program, and you can see also it sort of satisfies the condition of being a small unit, right? So the remainder list does nothing else but take a number n, take those n primes, compute their remainder mod 4, and collecting everything and returning it to wherever it was called. So the next procedure that I have here, called Chebyshev bias, is I can remove this so you can see it printed nicely in Maple's way of doing this, is a program that has the same simple-minded input and output structure. It takes a number n, referring to the number of primes that you're going to work with, and then it simply adds up some numbers. Whenever the n is 3 modulo 4, it adds 1, and whenever the n is 1 modulo 4, it subtracts 1. So it sort of keeps track of the balance between the mod 3 and the mod 1 primes. And so the way you can do it for 1,000, say, is that, so apparently what happens is that when you take the first 1,000 primes, first there's 2. That's not interesting because it doesn't play a role in the race that Chebyshev has designed. But then the remaining 999, then apparently there are 9 more that has remainder 3, then there are examples having remainder primes having remainder 1. Right, so this works in the obvious way of first taking n, then we compute the remainder list, which is like I just showed you before, and then I'm using here a construct in Maple that is also perhaps new if you are more used to more standard programming languages, namely a for construct with a list. So it works the following way. So I said for I in Cn, where Cn is the list, do the following. So essentially what it does is that it takes all the elements in the list and goes through them one at a time. So this in thing is not something I've seen in a lot of programming languages, but it works really nicely because it means that when I'm inside the for loop, then I already have the number that I'm interested in assigned to I. Right? So at the very center of this procedure, I will say, okay, if I is 3, then I add up my count of the bias, and if I is 1, I add down the count of the bias. So it's sort of either I go up or down. You can see this is an elif construction. So this is actually one that we use when we have many choices, and in a sense, the many choices that I have in mind here are the remainders 1, 2, and 3. Right? Because the point is that if I had done this with just an if, then the if else would say, okay, if I is 3, then we add up the bias, and then if I is not 3, we reduce the bias. Well, that would mean then that with 2, we would reduce the bias. And that's not really what we want. We want 2 to be left out. So we use elif to say, okay, if I is 3, then we do this. If I is 1, then we do that. And if I is 2, then we do nothing. Of course, for something like this to work, you better initialize the bias counter, and this is done at the very beginning of the program. Right, so this you can do, and then you can sort of, ask Maple to do these figures of the bias. So essentially, I've computed the Chebyshev bias until prime number 200. I can do that to, oops, I meant to do 1000 here. But you can also see that this is now pretty slow. So why is it so slow? Well, that is because I am extremely wasteful with my computations. So what is very wasteful here, and of course we're going to return to efficiency of programs later on, but let me just point out what the problem is here. The problem is here that whenever I'm computing one of these numbers, I'm starting completely over. Right? So if I want to know what is the Chebyshev bias of 1000, well, and I've maybe just before, like I would do when I wrote my, when I made my graph, if I do it just before with 999, well, that is more or less the same computation we have to do, because the way it works for 1000 is that we compute this list of 1000, the 1000 first primes, and then we do the computation. Right? If I have 999, I do the list of the 999 first primes, and I do the computation. Well, if I could somehow save the information that I already had in the first 999 slots of this list, then of course I wouldn't have to recompute it. And that is very obvious when I do the illustration of when I do the plot, right? Because the way the plot works is that we need to see all the values. So that's what I mean by saying that it's wasteful to do this only to do it in this way, because I need the Chebyshev bias at 999, I need it at 998, and so on. So why am I doing this recomputation? So I'm not going to try to solve this, but a fairly obvious solution would be to say, okay, we decide first on a number to which we want to do the Chebyshev bias construction or computation. So maybe we decide, okay, I'm only going to be interested in the first 10,000 primes, right? And then I run the remainder list on those 10,000 primes. Then I have that information and I store it somewhere in a global variable so that I can return to that all the time. And then to do the Chebyshev bias, I could work with that list. I could even be a little bit more clever. So instead of saying, okay, if I want to, now I don't have to look at primes anymore if I've stored this data once and for all. But of course, I could also say, well, to compute the Chebyshev bias at 1000, if I know it at 999, well, then that actually only involves prime number 1000, right? Because there's only one. I need to know it. I know it's going to be one more or one less. So as indeed it is here. So again, you could save a lot of time there. So and this of course comes up, right? It sort of depends, what I'm trying to do. If you want to disprove Chebyshev by looking at some fairly large numbers, well, the problem is now that if I put in 10,000, then that's going to take quite a while, right? And I could sit here and wait for 10,000, but I couldn't sit here and wait for 1,000,000. That would just be too slow. So of course we need to worry about these things, but the philosophy we have in the course is that first we write something that just works, and then later we go back and see if we can make it more efficient.